Okay, so I've written up a little example here for our next lesson on related rates. And this one, I'm just giving you the bare minimum of information. This is the information you'd see in a question that would be in your textbook or on a test. They give you, they would have to give you these facts. They give you an R value, an H value, and a dV dt value. And they might ask you, what is dr dt, or what is dh dt? And right here we're talking about this cone here. I just put up this cylinder here as an example. When this cylinder is draining out here, like this, at a certain rate, dV dt, the volume's decreasing at a certain rate, it's pretty easy for us to figure out how H is changing. Because when we look at the formula, the R value is never changing, but in the cone, the R value is changing and the H value is changing. So we have to do a little bit more clever thinking with the cone example. So to start, we'll want to write out the formula for its volume. V equals 1/3 pi r squared h. And so the first thing we're going to want to do is take d by dt of both sides, take that derivative with respect to time. However, we are going to end up with a dr dt and a dh dt in our answer. And what we want is just dr dt. So what we have to recognize is that if a certain amount of water or whatever substance drains out of this cone, to here for example, if our original radius is 10 and the original height is 50, then the ratio of the radius to the height will never change. It'll always be 10 centimeters to 50, or 1 to 5. R over H equals 1 over 5. And if you think about it, this is because you can look at the cylinder as a series of similar triangles. If you looked at it from the side, it would look like this. Oh, that's a little shaky. It would look like this. Look at the line tool here. Okay, perfect. So it would look like this. And so if we start out with a certain height and radius, if we decrease, no matter how far down we go, that ratio is always the same. And so we can take this ratio and have it apply for any volume. And so we can replace either r squared or h. But because we want dr dt, we'll want to get rid of the h variable. So if we multiply h on both sides and 5 on both sides, we're going to get 5r equals h. So just move this h over here. It's the numerator. 5 goes up to the numerator over here. 5r equals h. So we can take this and pull it right out of there and move this right in. So let's rewrite this. V equals 1/3 pi. Actually, this should be 5/3. We'll move the 5 over here. 5 goes right up there on top of the 5/3. And then we'll have r cubed. So this is a neater formula here. This will let us solve for dr dt. That's better there. This will let us solve for dr dt without running into any trouble. Now, this only applies, obviously, in this case, where the ratio of r to h is this 1 to 5, but if you have a problem similar to this, then you'll probably run into this exact type of problem with the cone So as long as you understand what we're applying here, we're taking this ratio of R to H that doesn't change as the volume changes in this cone, then you should know how to apply this once you see this. See what we're doing here. So that said, let's go right ahead and take a d by dt of both sides of this equation. So first side is easy, dv dt equals 5/3 pi. This part doesn't change because it's a constant. Now, r cubed, we're going to have to do our implicit derivative, apply our knowledge of implicit derivatives. So we do kind of like a chain rule here. We do times 3r squared. So derivative of the outside, and then go in like the chain rule. The inside's derivative is dr dt. Now, because this problem's asking us for dr dt, we should move this stuff over to this side so that we can get dr dt by itself. But first I want to point out that we have a division by 3 and a multiplication by 3 here, so we can just cancel these out. So we're left with 5 pi r squared left over on this side. Whoops, went off the screen there. So now let's go ahead and move it over. So now we can say dr dt equals dv dt. I'll make this sideways so we can read it more easily. dv dt divided by 5 pi r squared. Now, lastly, we just plug in the values we have, and it should just give us an answer. So dv dt is -2, and over 5 pi, that's easy, times r squared, and r is 10, so I'll just go ahead and square that. That's 100. 10 squared is 100. So we have -2, and I gotta move this again. I'll move this stuff over to get out of the way. Oops. There we go. Okay. So now that's equal to -2 over 500 pi. And we'll simplify it one more time, equals -1 over 250 pi. Now, let's go back and look at what we're really saying here. If we're saying that dr dt equals this value, we're saying that the radius is changing at this rate every second. And this makes sense. We're going to expect it to be changing at a constant rate. If this volume is decreasing trickle at by a certain amount of volume each second, yeah, we're talking about seconds here, each second, then what we're seeing here is the change in radius per time happens to be a constant value, where r is decreasing by so much every second. So for each unit time, each second, we're decreasing by this amount. So luckily enough, we're just about at the 10-minute mark, and this should have been a pretty thorough look at this example. I might do another one, or we might move on to the next section, which will be more application of derivatives. So thanks for watching, and I'll see you in the next video.